Okay. Hey, what's up, guys? How are you doing? I see a lot of familiar faces. That's a great thing. Jay, Daniel, right? You were at my last talk. Who else? Remember you. Sorry I didn't come to your talk. I heard it was great. Who was here at the machine learning talk? Okay, that was a really dense, kind of deep dive kind of thing. I'm not going to do that today. We're gonna do more of a survey talk today. We're going to spare our brains a little bit, but my hope is that by the end of the talk, you'll be able to take some of these high-level concepts and apply them to your own code base. So this is our agenda. That's our agenda. We're going to go over benchmarking, neural networks and matrix multiplication, CPU cache optimization, extensions, concurrency and parallelism, and multiprocessing for the embarrassingly parallel. Don't worry if you don't know what any of that means. We'll get to it. All the benchmarks on that I'm going to show here on an i7-8650, just a run-of-the-mill CPU, 16 gigs of RAM, 7.2 on Windows. Okay, so performance is the amount of useful work a computer can do in a given amount of time frame. To increase performance, either do more work in the same amount of time or do the same amount of work in less time. Which increments is faster? A little trivia here. Anybody know? The difference is this is a post increment, that's a pre-increment. Who thinks it's A? Who thinks it's B? Well, you'd be right. It's about, was that 0.4 microseconds per 1 million operations. This is just a toy example, but let's look at what's going on under the hood. So in PHP, we have these things called opcodes, where your PHP code is essentially compiled down into opcodes, which it gets executed by the Zend engine. So now, if we look at it, which one do you think is faster, A or B? Why is B faster? Less. We're doing less, right? Less work, same amount of time, right? For this example, because it's boring, really. It's just adding 8 elements to an empty array. So for operation 2, what we're doing was we're taking our carry array on the left, and then we're adding 8 elements to it for a total of 16 operations. Then in iteration 3, we have 16 elements in our carry array, and we're going to add another 8 to it for a total of 24 operations. And in iteration 4, we have 24 in our carry array. We're adding 8 to it. And so the number of operations is not growing linear here. So reduce and merge is not a linear operation. That's why we're seeing such a disparity between the two ways of doing array flatten. This is more like, I don't even know what that would be. That's more like exponential. Does anybody know? Anybody know what the time complexity of that would be? It's definitely not linear. Anyways, so why benchmark it? Well, I hope I've convinced you as to why you should test the code for performance. It's easy to make a mistake. It'll help you identify slow code, but you also want to set a baseline for future refactoring. So in the same way that you write a unit test for a particular area of code and then go to refactor it, and know that you didn't break it. You can do the same thing with a benchmark. You can refactor your code and know it didn't get slower. Or if you're refactoring specifically for performance, this is how you would know that you actually achieved what your goals were. So I recommend PHP Bench. It's a framework for creating glorious benchmarks. This is what it looks like. It looks just like PHP Unit in terms of the how the class is set up. We have a setup method, and in this case, we're instantiating just a 1 million element 2D array of the number 42. And then we have a method similar to how we would have in PHP Unit. This is the actual test. We leverage annotations highly in PHP Bench, so we mark it with the subject annotation. That means it's a test and not a setup method or anything else. Iterations means that we're running it for 3 times. And then we want our output in seconds with three decimal places in precision. And so I'll just run one of these real quick.
So you can use PHP Bench to basically, I guess what's the use case? You usually set it up like you would PHP Unit to run every time you update a function, just see did I improve or.
Yeah. So you could use. There's other things that you could use to measure performance, right? You could use a debugger or a profiler. What's nice about benchmarks in PHP Bench is it's part of your code base. So there's no, you can't say, well, it's right in front of everybody's eyes, and people will see it if code gets slower. They just run the benchmarking suite and they say, hey, this used to be quick, now it's, yeah. So,
Yeah, I was gonna say you could definitely.
oh, absolutely. In fact, there's assertions that you can make too. It's kind of weird though, because it depends on the hardware, right? How fast something is, but you can assert that something took less than a second or something like that. Who answered that question or asked that? Yeah. And so yeah, this is what it looks like to run that particular benchmark that I just did. Right now we're doing the array reduce plus merge, so it's taking a while. That'll eventually do its thing. And voila, okay, cool. So that's how you can benchmark your code. All right, so let's talk about Rubix ML. It's a machine learning library. We can do machine learning, deep learning. It's basically a tool that allows you to take your data, your company's data, or any data for that matter, and train a computer to perform tasks. I highly recommend checking it out. It makes you feel like a wizard, literally, when you use it. Anybody with a data set can pretty much instantly become an expert in some area with a computer. If you have a good data set, like I said, it's real fun. Makes you feel like a wizard. What is machine learning? It's a collection of techniques for gaining insight through data and computation. Computation is the main word there. We're going to be focusing mainly on optimizing computation today. And so now let's talk about neural networks. This is a graph of kind of shows the relationship between. Does this show up? No, it doesn't. That's weird. That's a high-tech TV. Okay, well that's all right. The x-axis shows computation in gigaflops, and the y-axis is accuracy. You can kind of see that the most accurate. Well, let's start with the least. Well, that's useless. The least accurate. The least accurate neural networks tend to do the least computation. The most accurate tend to do the most. I'm sorry. The most accurate tend to do the most computation. And in between, we kind of have this weird, kind of like diminishing returns curve, indicating that computation isn't everything. It's a lot of it, but there are ways that we can kind of skirt having to do a lot of computation through designing efficient architectures, essentially injecting prior knowledge into the architecture to achieve better performance. But this is on the ImageNet data set, which is a huge data set, 20,000 different classes of things like strawberries, leopards, cats, ship containers, stuff like that. And that's just an example. So just keep this in mind. This is the motivation for us trying to speed a lot of these things up, because the more computation you can do, the better, the more accurate you can be. So this is a kind of depiction of what a neural network looks like. Up to 90% of the computation in a standard feed-forward network is spent doing matrix multiplication. I'll explain what that is, but really all it is one function that's doing about 90% of the work in this. And so the way this works is, you can imagine this. We have layers of nodes. Each node is, you can consider it a neuron, which has it's connected to every other neuron by a weighted synapse. This weighted synapse is the weighted synapses are represented as a matrix in the algorithm. And so when we apply the inputs, you can think of those as the impulses applied to the first layer of the network. That operation is a matrix multiplication. It's followed by what we call a nonlinear activation function. After that, we'd apply another matrix multiplication. Just keep doing that. So matrix multiplication is pretty important for what we're doing here. This is what it is. We just take a row of A and a column of B. We multiply them together, and then we sum them up, and we put them in matrix C. I'm not going to stick too much on that. It's really not a math talk here. But this is what a naive matmul implementation looks like in PHP. The reason why it's naive is because it totally disregards the CPU cache. The problem is with this right here, this B, how we're traversing B, and that will become more apparent. But this runs pretty slow, about 7.5 seconds for about 1 million operations. Okay, any questions so far? Good. Now we're going to talk about cache optimization. Why cache optimization? So as of 2010, the speed of memories compared to that of processors is such that cache misses rather than actual calculations dominate the running time for sizable matrices. What does this mean? Well, the CPU is way faster than the rate that we can get data into the caches, basically. So it would behoove us to design programs or design algorithms in ways that optimized for the cache, that kept data that it needed in the cache when it needed it. And so in order to kind of understand how we can apply this in PHP, we'll look at how arrays were implemented under the hood prior to PHP 7. So the way that they worked is we had some key or some index that hashed to a bucket, and so this is a hashing function that basically takes the index and turns it into an integer that has a bucket at the end of it. And you can think of the bucket as the head of a doubly linked list, basically. It's the first element of a list. And the reason why it's a doubly linked list is for collision resolution. So if two keys hash to the same bucket, we can just tack on the element to the end. So there's no collisions, in other words. And so if you know anything about a doubly linked list, they typically have terrible cache performance because every element is a separate memory allocation. So when you add something to a linked list, chances are the place that it gets allocated in memory is nowhere near the data that is in that array. That'll make more sense when I get into another slide. So the order in a PHP or prior to PHP 7 array was maintained by a doubly linked list as well. So PHP arrays are ordered hash maps, so it doesn't matter what the key is. It can be 3, 2, 1, but the order is still maintained, and that's also maintained by a doubly linked list, and that will matter when we do cache optimization. So what are the limitations of this design? Well, first of all, buckets and their contents both require separate memory allocations, so they're going to be in different locations spatially in memory. And so that's not good for the cache because typically when we retrieve items for the cache, we retrieve blocks of memory, not just single elements. And so chances are we're really not retrieving any data that we can use in the future for a computation if we're just retrieving elements singly. And also traversing a linked list is a random memory access pattern. So what that means is, like I said, there's different allocations all over memory. When we're traversing it, we're literally just pointer chasing through memory, and that's terrible for the cache. So what were the changes in PHP 7? Well, buckets are stored in a C array now. We're no longer using a doubly linked list, and the ordering is maintained inherently in the C array. So arrays are naturally ordered, so we don't need to have a separate doubly linked list for that. It also means greater cache utilization because we now have a linear memory access pattern instead of a random access pattern. So random would be just kind of pointer chasing, but when we allocate an entire array in a chunk, it's just a whole block of memory. So what we can do is when we retrieve the first item of that array, the entire array gets loaded into cache. So that means we'll have cache hits for the next few computations as long as we're traversing it in a linear fashion. But this does mean higher memory usage because we have to allocate these arrays in chunks. Specifically, they're allocated in powers of 2. So starting at 8, so it'll be like 8, 16, 32, 64. It's not as easy to add and remove and just tack on an element to an array in a C array like it is with a linked list where you just kind of move some pointers around. So we actually have to do some fancy things to get this working, and it does result in higher memory usage. And the second thing is that scalars are embedded directly into the array, and that gives us greater cache efficiency because when we traverse it, we kind of just, like I said, just grab all this memory at once, and it's in the cache and it's ready to go. So here's a cache-friendly version of matmul, and you may not, I guess if you stare at it, maybe it'll make sense. This top line transposes an array. What that means is it changes the rows to columns. You can think of it as changing row from like row major format to column major format. Trust me, it works. Then we just perform the same thing just with that transposed array. And I'll show why that is actually going to matter. But this gives us a 2.27 X speed up just by doing that transpose before the computation. And so that, in terms of where we're at, in terms of other PHP libraries, Math PHP, I don't know what they're doing. They're out of there. They're creating like objects within that loop, which is not what you want to do. You usually don't want to create objects in a loop. It's just a lot of overhead. PHP ML, they're not quite there yet, but we can do this, like I said, about 3.3 seconds. And so this is what's going on underneath the hood. So in the naive implementation, the first array we traverse it in its natural order, or its row major format. But in the B array, we're traversing it in essentially column major format. So I really wish this worked. So when we load this element, we're also loading this array, but we don't need that data. So that's stale. That's just stale cache data. The data that we do need never gets loaded into the cache. So we not only do we have nothing but cache misses, but we also load data that we don't need into the array. And then the transpose version, we're now traversing the B array, their B matrix in row major format. So now we're getting cache hits, nothing but cache hits. Any questions?
So
Make sense?
Can you go back to that code, the PHP code example?
Yeah.
I don't have to understand all this, but basically, because you're performing an operation on two arrays, right? That's what's going on. Like the transposition actually helps you compare them and keep things in cache.
It's just for the cache, just for the cache. Yeah. There is a side effect too. There's a side benefit, and that is you don't need to index into the B array. Well, you do, but you don't need to index into it twice. And so there's a little bit of speed up there, but it's mainly due to the cache characteristics, I guess you can call it. So I mean, the algorithm's the same. It's still an order and cubed. You know, we have an inner, we have an outer, we have a middle loop. So we're still doing the same amount of operations. It's just that the data that we need, or the data that the CPU needs to make this computation, is available in cache when it needs it.
You don't get in PHP, because it's a pretty high level language, any sort of control over telling it how to cache things, right?
No. No, and you usually don't get that in other languages either. Some languages are smart enough in the compiler to do what's called loop transform, and it will, like for example, flip some of these loops so that it does have better cache characteristics. It's hard to do that in PHP. You kind of have to know. So you kind of have to know. That's why I mentioned about the PHP array and how it's implemented underneath the hood, because you really need to know how it's implemented under the hood to take advantage of this stuff. And I'll give you a quick hint at the end of it that'll kind of just. It's like a rule of thumb that you can just go by. Actually, it's this one. Here we go. Rules of thumb. So always traverse array in its natural order. And here's a hint. For each always does this. If you're using for each, you have nothing to worry about. It's always going to traverse the array in its natural order. Also, and if it's not, if you can't do natural order traversal, you can perform loop transformations, either transposing or flipping the inner and the outer loop, to get it that way. Cool. Any questions about CPU cache optimization? All right. PHP extensions. So extensions are pre-compiled libraries that provide objects and functions that can be accessed from PHP userland. They can either be statically linked at compile time into the PHP binary, or they can be dynamically linked at runtime. You just put it in your PHP ini file that you want to load it. So why would we do pre-compilation? Well, we don't have to do runtime type checking. So if you know anything about a dynamic language, we don't know what type the variable is going to be until we start running the program, really. So we have a ton of overhead when we do type checking. We also get additional compiler optimizations when we do compilation. For example, what I think is one of the cooler things, discovered parallelism. So the compiler will actually say, hey, you know what, this loop, it looks like we can do some of these operations in parallel. So what vectorization is when we just take, let's say we have a vector of numbers and we want to multiply that element-wise with another vector. It'll say, hey, we're just doing a bunch of multiplications here. Let's just execute one instruction with 8 floating point numbers, and it counts as one instruction rather than 8. And so that's called vectorization. That's also called SIMD sometimes for single input, multiple data. Also function inlining, which is basically where the compiler will take a function. Let's say you're making a function call in a loop. It'll replace that function call with the actual contents of the function, so we're not calling the function all the time. And we get access to low-level libraries as well that are usually highly optimized. So what are some of the trade-offs, pre-compilation versus interpretation? Well, I would say one of the biggest things with interpretation is that our development rate is fast. We can literally just run the change the second that we make the change and see the results. Whereas with pre-compilation, we have to take the extra step to compile the code into a binary. But we get better runtime performance. So there's this sort of inverse relationship between the two. So now I'm going to introduce Zephir. Zephir is a PHP-like language. It looks a lot like PHP, and I'll give you an example. But it compiles down to a PHP extension. And the way this looks is we have our Zephir code that gets interpreted to C, or compiled down to C rather. That gets compiled by your C compiler, and then that executes a CPU instruction set. Why Zephir lang? Well, it's dynamically and statically typed, so we can use dynamic variables like we're used to in PHP, and we can also use statically typed variables like we're used to in C. The benefits of using statically typed, well, I think I gave you the benefits. We don't need to do type checking. Also, memory allocation, garbage collection is done automatically. One of the hardest things, I would say, coming from like a high-level language to C is memory management. You don't have to do any of that with Zephir. It abstracts that entire thing away from you. And it looks and feels a lot like PHP. So here's matmul in Zephir. I'd say probably the biggest differences here is that we're declaring a static variable there. That sigma is going to we're going to use that to accumulate the products of the two rows, or the row of column A and the column of matrix B and the row of matrix A. There we go. For loops look a little different. We have this arrow there instead of a colon to mark the return type. But in general, it's very PHP looking. And with this, we get a 5.4x speed up just by compiling the same algorithm down into a PHP extension. And so the way that looks is now we have this is the extension right there. We do it, like I said, about 1.5 seconds. So rules of thumb: port performance crucial code to an extension, but don't port everything. Don't overdo it, because again, it's going to slow down your development time. Just take the bits that really matter, and you can make an extension out of it.
How long does it take to compile a PHP extension? It probably varies by machine, but just curious, like rough estimate.
Yeah, and also the size of the extension too. So Tensor, which is the extension that we wrote for Rubix ML, which basically you just install it, everything becomes faster basically.
Okay.
That takes about 30 seconds, I would say. Yeah. Which can be like forever, right? Because they're like, oh man, does this work?
Right. Yeah, if you're
So.
that sucks. But if you're just doing it every
Right.
once in a while.
Yeah. Yeah. So any questions about PHP extensions? Nope. Good. By the way, if you have any questions, ask them now. If it's going to lead us on a tangent, I'll just delay it. But I usually say it's better to kind of get it out of the way now. So now we're going to talk about concurrency and parallelism, which, we'll get into it. So this is what a serial program looks like. A serial program running on a single thread. So let's say we have our main program, and then we want to do a database call. The database call will say, great, I'll get that information for you. Just wait 1 second. We'll wait a little bit, and it'll say, all right, great, we came back, we got that data. Main program continues. Now we need to make an API call. The API call will say, hey, great, I'll get that right for you. We'll wait a little bit, and the API call will say, all right, I'm back. Here's your data, and we can continue from that. The problem with this design is that we have to wait during this time. We could be doing other things. And so what a concurrent program looks like is something like this. So maybe our main program will go to the database call and say, hey, I need this data from the database. The database call will say, great, I'll get that right for you. But instead of making you wait, it's going to say, all right, I promise that I'm going to get you this data. So it hands it back a promise. And then the main thread says, okay, great, that's good enough for me. Does the same thing with an API call. The API call says, great, I'll get that right for you. Here's a promise. Main thread says, great, I'll take it. And so the difference between serial and concurrent is that while the database call and the API call are doing their thing, the main thread can continue doing other things. and so we can compress the, we don't need to waste time by waiting. And so concurrency is when a program is managing multiple tasks at the same time. The key word is managing. So what do we need to build concurrency? First of all, we need promises. We need a way of saying, here's the future value of something. We need non-blocking I/O, because if we had blocking I/O, it wouldn't matter. We would have to wait for it anyways. I didn't want to spend too much time on coroutines, because it really is, it's kind of like an ancillary topic. The reason why we want coroutines is because they essentially make writing asynchronous code a lot more clear. It allows you to write asynchronous code like it was synchronous code, in other words. And so AMP is a concurrency library that does just that. They use coroutines under the hood to essentially make it more readable, to make it easier to reason about asynchronous code. Because one of the things about asynchronous code is it's not often easy to reason about. You're often like reacting to things rather than just telling the computer what to do, and so it's kind of it's harder to reason about. So why AMP? Well, it provides all the concurrency building blocks that we need, which includes promises and also non-blocking versions of many of the PHP functions. One of the dirty little secrets of PHP is that pretty much all the functions are blocking. So things like database calls, file get contents, they're all blocking. They weren't really designed for an asynchronous world, and AMP, fortunately, they provide us with most of those tools. It also uses coroutines for better code readability, and it has a rich ecosystem. So HTTP server, WebSocket client, and also this library Parallel, which we're going to use now to speed up an example from machine learning. But first of all, what does a parallel program look like? This is an idea where we have some main program execution. We come to a part where we can split the task, let's say the main task, into as many smaller tasks as we want. In this case, we have 3. So there's a forking process. And then we execute those subtasks at the same time. And then there's a joining process at the end where we kind of like concatenate everything back together, and then we can continue on with the main program. And so this even further smushes all the computation. This time we need multiple cores, because in order to do this, we need to actually execute these operations on different processing units. So what is parallelism? Parallelism is when a program is split into subtasks and processed simultaneously. That's really all it is. What do we need for parallelism? We need concurrency for one. We need a way to manage things that are asynchronous, things that we're waiting on. We need some form of inter-process communication, which can either be message passing, which is like, I'm going to serialize some data to you, you're going to unserialize it on your end, and then do the same thing in reverse. Or shared memory, which is where we allocate a chunk of system memory, and we say we're all going to use this memory to kind of communicate with each other. It's harder to do shared memory. You need things like mutexes, and you can do there's race conditions, and there's all sorts of things that can go wrong. In PHP, we generally use message passing, but we can also do shared memory with an extension called Parallel by Joe Watkins.
Where are those messages stored when you say passing? Are they in memory, or are they actually on the CPU?
Yeah, I actually have a slide that kind of will give you a better idea, but so yeah, a message would just be like a DTO, like a data transfer object. It's just here's some data that you're going to need, and then you can pass me back some data once you're done computing, something like that. Concurrency. First of all, they're not the same thing, and some people get these confused. They're very similar in the English lexicon. They almost mean the same thing, but in computer science they're different. So when do you want to use concurrency? You're going to want to use that when you're I/O bound. It gives you nothing if you're CPU bound, because we're still only using one core to do concurrency. You want to use concurrency when you have multiple tasks that you're waiting on that you don't need to necessarily wait on to continue doing other things. Parallelism, on the other hand, you want to use when you're CPU bound, when you just need more compute, and that's the example that I'm going to show you. You do need multiple cores, and concurrency can be thought of as non-deterministic because you could take the kind of like the subtasks, we'll call them, and execute them in any order, and you'll get the same result. Whereas in parallelism, you have a deterministic outcome. The whole goal is to take one task and have have it always be this, the same output, just run on multiple cores. And so lastly, we're going to talk about multiprocessing for embarrassingly parallel. So embarrassingly parallel is a problem that requires little or no modification to split it into parallel subtasks. That's why it's embarrassingly. Here we're going to look at an algorithm called random forest. And so within this algorithm, there's a number of what we call decision trees that are basically kind of like, imagine we have a basket of fruit up here. And we want to divide the fruit such that, and we want to come up with a set of rules such that as we traverse this tree, we separate the apples from the bananas and the pineapples and whatnot. And so we need some rule set. We need to induce some rule set into this decision tree such that the where this node is, it's homogeneous. There's only apples in there. Ideally, we'd like it to be homogeneous. Same thing with bananas. Every once in a while, we might not quite separate them fully, but yeah, the idea is to separate them as good as possible. And so there's an algorithm that does that. I'm not going to get into it. This is a random forest. So is that. What a random forest is basically just a bunch of these trees, and they each make a prediction about what it should be. Should it be an apple? Should it be an apple or a banana? And those predictions are then averaged into, and that helps basically to reduce the variance of the predictions of a decision tree. Why do I bring this up? Is because each one of the task to grow a decision tree can be done in parallel. And so this is what it looks like. So let's say we have a bunch of grow tree tasks. We have 10 of them, and we have 4 cores on our CPU, let's say. So we spin up 4 workers, which are, so the task queue and the worker pool are both part of our application, and they're running concurrently. And then we have 4 PHP processes that are running separately. So these are 4 PHP interpreters running as different processes on our computer. And what we do is we just multiplex the tasks over the worker pool. They're assigned first come, first serve, basically. And as soon as a worker is done, as soon as the worker gets the information back from the process, it says, okay, I'm ready for more work, and we assign it another task. This inter-process communication, like you had asked about before, so what's going on there is we're serializing blocks of data and passing that to the PHP process. It does its computation, and it serializes whatever we need back. Any questions about this diagram?
I'm kind of curious because I don't know internally how it works, but how different is this from the process of how like PHP FPM works when you have multiple child processes running? I know that's for web requests, so it's like that part's different. But like, is there a similarity here, or do you know?
Yeah, I'm probably not an expert to answer this, but what I do know about I know Nginx runs on threads, so I know that they have like a thread for each request.
Yeah.
And I think there might be an instance of.
Yeah, I assume the way that works is like they have Nginx has a thread for each request, and then it passes.
And there's an interpreter, I think, that.
FPM, the process manager that like has a bunch of shit like child workers.
Does anybody know?
I don't know.
Yeah, I don't know for sure, so I don't want to,
Future talk.
Yeah, right. Any other questions about this diagram? Oops. Okay, cool. So here's the result. PHP ML is another library that does kind of the same thing as not the same thing. It does a lot of the same things, just slower. So this is running on 4 cores in parallel. This is running on 1 core in serial. You can see it takes about 7 minutes to do a 92,650 sample data set. So these are Dota 2 games. Does anybody know what Dota 2 is? It's a game. Yeah, so the task here is we want to predict the outcome of the game. And so we take 92,650 sample games. We take the way it works is there's heroes, I guess, and so we take the heroes that were as part of the team, and based on that, when we know the outcome, and based on that, we can train a random forest to essentially predict the outcome. And so we're a lot faster, especially running on 4 cores, and we're also more accurate too than that other library. We're about, it's still not great, but it's better than about just a little over half the time were correct. So yeah. Okay, cool. So good news. Rubix ML, we just had our first release candidate. It's been about 2 years, about 1 year in alpha, 1 year in beta, and about a week ago I just tagged the release candidate number 1. So we're finally getting to the point where we're almost stable. We've been in production for over 1 year with no problems. I've had a neural network running on our website, no downtime or anything like that. And we also got our first large commercial customer too. They're using it to essentially predict the lifespan of various components of cooling towers. So what's next? Well, we got Rubix 1.0. We plan on integrating things called BLAST routines, but BLAST stands for Basic Linear Algebra Subprograms. They're basically highly optimized Fortran routines that we can integrate into our tensor package, which was the linear algebra extension and library, and we would see just orders of magnitude improvement on what we already have. I mean, these things are cache optimized, multi-threaded, all sorts of optimizations go into these routines. And so that will enable large-scale deep learning. We're already doing deep learning right now. We can do things like computer vision on a basic scale, but this would really, really get us to the point where we could do computer vision, natural language processing, and a lot more things on bigger data sets. And then we're working on a fixed array, a fixed or strided array implementation. What this is in contrast to the PHP hash map, this is actually just kind of like just a chunk of memory that you allocate all at once. So if you can imagine a matrix with 1 million elements, we just allocate all that memory in one chunk, which is really nice because we get the best cache efficiency. And that's also what BLAST routines expect. They just expect a chunk of memory. So there'd be a lot less overhead with that. Any questions? This is my last slide. All right, that's it. That's me. That's the GitHub repository. Feel free to email me if you guys had any questions or anything like that. I'd be happy to take questions now. Other than that, thanks for listening.